you, I guess all of you know that. We completed last week the reinforcement learning. Most likely you will have like probably a programming assignment which sort of connects what I'm going to do this week as well as reinforcement learning, which involves using the MDP programs that you already have written. Okay, so to see efficient approaches to doing it. Okay, that will come soon enough. So what I am going to do today actually is, so we talked about Markov-Decision processes, and we looked at them first as a pure inference problem, which means you're given the model and you're trying to find the optimal policy, and then we looked at learning the model, which is the reinforcement learning. Now we'll come back and actually look at how to solve some of the ideas for solving large-scale MDPs more efficiently. Okay, so the idea is value and policy iteration are the bedrock algorithms for Markov-Decision processes, except oftentimes they're polynomial, first of all, in the number of states, and oftentimes for normal problems, the number of states is just too high. And so you want to be actually able to drive down the computational effort in computing the policy. Okay, so we'll look at what are the approaches, and in some sense, you could have done this aspect right after MDPs. But I did MDP, we did the MDPs, then we did the reinforcement learning, and then we are coming back to MDPs and look at more efficient methods. And part of the reason is, as I mentioned in last class, basically many of the reinforcement learning approaches can actually be used as approximate methods for solving MDPs. So if you have a very large model, rather than use the model using value and policy iteration, you might actually just try to use reinforcement learning kind of techniques, okay, wherein you just use the model almost as a simulator of the world. Okay, and as I said, motivation for that essentially is sometimes by doing this, hopefully you might be able to get faster answers to what action must I do in the current state than you would if you have to compute the entire optimal policy. Okay, that's the idea, yes.
So a second ago you said that value and policy iteration were polynomial number of states. Are you talking about a single step or the entire algorithm?
The entire algorithm.
I thought it was unbounded.
What?
I thought it was unbounded but guaranteed.
No. So the complexity itself can be shown to be polynomial in the number of states. Okay. The specific algorithms that you have. So there is a problem complexity and the algorithm complexity. Mm-hmm. Okay. The problem complexity for MDPs can be shown to be polynomial in the number of states. Mm-hmm. Okay. Value iteration, you cannot bound the number of iterations. And so that particular algorithm doesn't look like it's actually finite. Mm-hmm. Okay? So I don't know whether that answered your question.
It kind of does, okay. Yes. And then policy iteration, that was exponential, right?
Policy iteration is exponential in, the number of policies are exponential in the number of states, yes. Okay. Yeah, so anyway, so we are going to look at more efficient approaches for doing inference over MDPs, and from here on, the reinforcement learning aspect and the inference aspect will be tied together. Okay, so you just need to know when am I doing more like learning, when I'm doing more like inference. Okay, so that's why those two topics came earlier. This is sort of the agenda for the next couple of classes. So to get higher efficiency, we do basically two different things. We can think of two different things. One is essentially consider heuristic search ideas. such as the kinds of things that you learned in A-star search, okay? And try to find out, in some cases, heuristic search can, for example, be helpful if you are actually, if you know the initial state, for example, then you don't need to find the entire policy, you only need to find the policy for the states that are likely to be reachable from the initial state. Okay, and in particular, actually, as I'll say in a minute, for most of this discussion, we will actually do the discussion in terms of SSPs with initial states. So SSP, by the way, is stochastic shortest path algorithms, and we talked about the fact that SSPs can be thought of as more general than infinite horizon MDPs as well as finite horizon MDPs. Okay, they're sort of indefinite horizon MDPs. Okay, and then we'll also think in terms of SSPs with initial states, because in fact in many planning problems you may well know where you're starting from. Okay, and so you know the state from which you are starting, and you still have uncertainty in the actions. Okay, so you really want to know the policies. The policy needs to be just partial. It only needs to tell you what to do for the states that you are likely to reach, starting from the initial state. Okay. So one idea for improving efficiency is use the fact that you're starting from the initial state and then do heuristic search ideas. And there are at least two very nice algorithms about it. One is called LAO star and one is called RTDP. And we will look at RTDP is real-time dynamic programming. And we'll look at real-time dynamic programming because I actually mentioned it partly last class. And we'll actually look at it in more detail. As I mentioned last time, RTDP actually came from reinforcement learning community. But you're using RTDP actually to avoid having to use the entire model. So basically you're being lazy, okay? But we'll actually see that one of the interesting things is, so we'll understand what RTDP would do if you know the model completely, and in what ways can you actually improve normal RTDP idea now that you know that you have the entire model. Okay, so we'll see that today. And then, so there's these heuristic search ideas, and there are also ideas based on online search. That means you essentially, rather than find the entire policy, you just find what to do from the current state. And then do that action, and then see what actually happens, and then decide what to do from that next state. That's more of an online decision making, okay? And there, in essence, you are not going to compute the entire policy. And in fact, there is no guarantee, in some cases, there may not even be a guarantee that you will actually converge to the optimal policy. You are essentially just trying to compute what's the best action you can do from that current state, okay? And there, we'll look at two different ideas. One idea is essentially based on what's called determinizations. We'll get to that probably next class. So the idea there is, sort of from an intuitive level, you start, let's say you're at a particular state here, you're at some state here, you can do either, action A1 or action A2. Okay. Now suppose it turns out that action A1 can give rise to multiple states with different probabilities, and similarly action A2 can give rise to multiple states. Right? And so in some sense at the online level you are sort of trying to figure out which action to take from this state. Okay? The deeper you can do this tree, the more information you will have as to what happens at the leaf level. One way of, in some sense, that picture is common for most online search as well as RTDP idea. One way the determinizations will change, and we'll get back to it next time again, is you start from here and you essentially you will ask yourself what would be the closest path from, if I was, sorry, let's see, if I am in state S1, these are the possible states that you have for these actions. And you can essentially determinize, in the sense, act as if the actions are actually going to have deterministic outcomes. Okay? And when you are deciding that, you can decide whether to assume that they'll have their most likely outcome, whether they will have all possible outcomes, whether they'll have outcomes based on the way you sample the actions. Okay? And the reason you go through this is this way you can then compute generate a deterministic planning problem. And there are very efficient techniques for solving deterministic planning problems. So you relax the stochastic planning problem into a deterministic planning problem, solve the deterministic planning problem, use that to figure out which action to take here. Okay, so those are called determinization-based approaches, and we will in fact look at this next class. Again, since I may have confused you because of the way I discussed this, so here is an extremely simplistic way of doing determinization-based idea. Okay, which is you are given you're working in a stochastic environment. Okay, what you might do is you are given a state. You're in the initial state, and you need to go to some goal state, and you've been given actions which have stochastic outcomes. Okay, go ahead and determinize all the actions in So basically, for an action which has S1 and S2, let's say this is 0.7, this is 0.3. For once, let's assume actually that you just took most likely outcome. That means action A1 will only give you S1. And similarly, action A2 might only give you S4, according to this determinization. So now you have a deterministic planning problem. You generate an entire plan for going from current stage to the final state. Okay, now you execute the first action of this plan. If you get the state you expect, then you execute the next action. If you continue to get the state you expect, you get, do more and more of these actions. Whenever you do not get the state you expect, right? Because once you generated a plan, you know what states you're expecting. If you don't get the state you expect, you replan. Okay? Now, in fact, it's been called, in fact, one way of handling stochastic worlds, I may have mentioned this, I hope I did. Stochastic worlds is replanning. So ignore the stochasticity, act as if it's a deterministic world, make a plan. If the plan fails, replan. Okay? This advantage of this is, of course, it just completely depends on deterministic planning technology. Okay? But obviously, even as I said this, you could see 10 million ways you can kill such a planner. Right? Because especially if you have domains which are what? When will replanning die?
When it's non-ergodic?
Exactly. If you are in non-ergodic worlds, then you don't get to say, oops, I made a mistake. You're dead. Okay? But even if you are in ergodic worlds, there may still be high penalties for getting into bad states. Okay? Completely ignoring probability seems too silly an idea. So, if this is one extreme, which is just ignore all probabilities and do replanning, another extreme, a better idea might be somehow do the determinization such that it takes the probabilities into account in interesting ways. So we'll talk about those kinds of approaches. The reason that sort of thing became interesting is at some point of time people started having competitions for large-scale MDP solving in planning community. Okay, and the very first planning competition, basically bunches of people introduced obviously their favorite value iteration, policy iteration, exact approaches for value and policy iteration and so on. And the way this particular problem was set up, once again I'll mention this when we come back to it again, you would actually be given the current state of the world, you tell the simulator what action you want to do, the simulator will do the action and tell you what the next state is. And it'll let you do it until you reach the goal state. And they'll see how many times you reach the goal state. Okay? And if you die in the middle, then you die. Okay, so basically they count the average success, where you being your planner. Okay? They set up a competition like this, and then they found that the first year, there was one group essentially tried just to be on the safe side. They had a very interesting, theoretically pleasing, technically challenging idea for computing policies. But they also thought, why don't we just throw this in, because this is a straw man, and we should basically at least say we do better than do better than replanning strategy, normal replanning strategy. And so in particular, what they would do is they made this straw man system called FF replan, which calls FF, which is a deterministic planner, and then just replans any number of times whenever it finds that it didn't reach the state expected. And they did this honestly just as a straw man. They didn't want it to win at all. And when they introduced the planner in the competition, that won over not only their planner but all the other people's planners, which made the community take seriously these kinds of ideas, determinization-based ideas. Okay, it turns out FF replan essentially, by doing well, made people say that there is an advantage of relaxing the stochasticity away and using the deterministic techniques. And there are a whole bunch of interesting ideas that came from there. One we will talk about from FF replan is what's called FF half with FF with hindsight optimization, where you take the probabilities into account in deciding what determinization you come up with. Okay, so that's another type of an idea. And one more idea which you can think of here is, again, if I have this kind of a tree, I just basically take samples all the way until I hit a goal node. I just one sample, okay, and then back up over that sample. And take one more sample, back up over that sample. And if I just do this sampling, that's called UCT technique. And it's essentially a sampling-based idea, and you won't really need to do sampling if you essentially have the full model. There's no real reason to do sampling when you have the full model. Okay? However, it turns out that UCT-based techniques will allow you to do better if the model is just too complex. Then you're using it more like a simulator. So we'll also look at those kinds of approaches. Yes?
So are you essentially running multiple Monte Carlos in parallel and then choosing the best one?
No, we'll look into the details in a minute. But okay, but basically, it is again. So just as RTDP is a type of a reinforcement learning technique, we'll see in a minute that corresponds to backup using the Bellman backup. This is Monte Carlo style reinforcement learning technique. Okay, and one of the interesting things is when you look at UCT techniques, you will see they will have exploration factors built in. And the exploration is exploring the rest of the model. Okay, basically, and so they are really a reinforcement learning technique, just using it directly in the case when you know the model, even though you know the model because you're just lazy to use the entire model. Okay, and the reason I'm bringing these are some of the best approaches currently for large-scale MDPs. Okay, and to give you a feel of the uncharted territories that we are in, these are slides from a tutorial that these guys, Mausam and Kolobov, gave this AAA 2012. And in fact, I would talk to you about a version of RTDP and a version of UCT for MDPs in this class, hopefully. And then your question would, a reasonable question to ask is, if you can do both of them, which one is better? And it turns out the paper, one of the first papers comparing those two approaches also appeared in this AAA. I'm not saying that paper is like the greatest thing since sliced bread, but I'm basically saying that you're very close to the current state of art now. Okay, policy iteration, value iteration, these are 1960s ideas. Okay, which in computer science is sort of ancient history. And now we are now in 2012 already. Okay, so which also means that I would sound increasingly less sure of myself. And and I will basically hope that in many of these cases you'll actually have to read papers. And in fact, one of the ideas I'm going to try to do is I'll actually get you to read at least 2 papers as part of these discussions, 2 conference papers. And the way we'll do that is I'll give you the paper, and then before you come into the class, you have to write a review of that paper. a one paragraph review of the paper. Since we have sort of discussed the paper here, you're just sort of looking for more interesting details from the paper. Okay, so I will get you to read one paper which compares, as of my current thinking, one paper that compares LRTDP and UCT, which is from 2012. And the other is this FF-half, which is this determinization-placed paper. Okay, so those are the two things that you will read. Most likely the UCT one you would read after this class and before that stage. Okay? So that's the whole one way of improving efficiency. Another way of improving efficiency is sort of realize that all these approaches are essentially, you first understand any approach at the state space, at the atomic level. Okay? Another way of improving it is to start reasoning at the factored level. That means you start thinking of states as made up of state variables, and you then have to talk about how do you effectively represent actions in such a scenario. So if you have state variables and if you have an action applied to the state variable, then it will change those values of the state variables. How do you model this change over the state variable values? We'll look at two ideas. One is a two-slice temporal base networks, and the other is probabilistic strips operators. Okay? Those are just two languages. The moment you start talking about atomic, there's no requirement for a language. It's atomic. State is an atom. Okay? But once you start going to factored levels, you need to start talking about approaches for representing the state, representing the actions, and then also representing the value function. Previously, everything was a big table. Now, so when you get to the factored side, the kinds of things that you need to represent, are, as I said, you need states. You will see that states are in terms of state variables. Actions, and we'll see at least some two possible approaches is one is a two-slice temporal base network, the other is probabilistic strips. We'll see what the difference is. And then you still have value and reward. Okay? And the value function was a big table before. For each state, it's a vector. For each state, what is the value? Okay? Now, states don't have numbers right now. States only have properties. So what you would like to do is write this value function compactly in terms of the properties of the state. So, for example, I might say, if in your state, the state variable SV1 is true, then go this side, false, you go this side. Then, if the state variable SV100 is true, go this side, false, go this side. If it is true, the value is 7.0. If it is false, the value is 3.0. And SV1, if it is false, the value is 9.0. Now, by just saying that, I've given you that. If I say this is the entire value function, that's it. So basically, it turns out, according to this, most of the properties of the state don't matter at all in deciding its value. Which is not surprising. In real world, actually, there are a large number of irrelevant features for states. Okay, and because all these features are being considered in computing the size of the state space, you essentially wind up learning the value of nearly identical states modulo the irrelevant variables many, many times. Do you see what I'm saying? Okay, again, it's not for no good reason that I keep saying things like, if your state is defined in terms of the color of your shirt, the length of your hair, etc., and the final thing that I'm trying to figure out is the probability of you passing this course, you will assume some of these variables are going to be irrelevant. But essentially here you will figure out which state variables are, as part of the policy and value iteration, you will figure out which of these variables are actually relevant, which are not. Okay, so you will start with a value function in this kind of, here is one compact representation. This representation is called ADDs, algebraic decision diagrams. Okay, so you might write an ADD representation for the value function, and then another ADD representation for the reward function, then the interesting thing would be to write the Bellman update directly in terms of these ADDs and the 2TBNs and P strips, the probabilistic strips. If you do that, then in one fell swoop, you would be computing the values for many, many identical states instead of having to do it many different times. Okay, and that's the idea of that's the advantage of factored representations, and we'll talk about that a little towards the end too. Okay, yes.
So these are just applicable to the actual reward functions themselves, but they have nothing to do with transitions.
The transitions are the actions.
Yes, they're the actions, but we can say, or could we, I guess, say that an action depends on the condition of a certain state variable?
Yes.
Okay.
That's how we, basically these representations, for example, the 2TBN representation might say, for example, that the two time slices is before action, after action. Okay? And each state variable is there in before action, and there is a copy of it after action. Okay? And then, so here is SV2, and then an action might say, for SV2 actually depends on SV1 and SV3. That's your Bayes network.
So
then the question, of course, is if you remember your Bayes network, then I need a CPT here, saying if SV1 is true, SV3 is true, what is the probability of SV2 being true, and what is the probability, and similarly if SV1 is false, SV3 is true, what's the probability, etc. So giving those would be the specification of the action.
The transitions themselves, though, can depend on state variables which we've just declared are irrelevant because they don't.
No, we don't declare anything irrelevant. The whole point is, I will give you the actions. I'll give you the actions and the reward function. The Bellman updates will eventually make you realize that certain things are irrelevant. I don't declare anything irrelevant. If I did that, that's sort of feature selection idea, where I'm going, jumping ahead beforehand. But no, that's not what I'm doing. Okay? Again, this stuff and this stuff is what we're going to be doing in the next couple of classes, or little more than a couple of classes. Okay, so just to give you an idea of where we are going. Okay, if you're lost, come back to this slide. I mean, I'll show you multiple times this slide, but these are the reasons. These are all grab bag of approaches for improving, large-scale MDP solving. Yes.
Sometimes it is observed that while calculating the value function of MDP, two states get the same value. So it can be concluded that those two states can be replaced with only one state, and
basically what they would do here essentially is, for example, if there were 100 state variables, and if this is the optimal value function, then what did we just found? That when SV1 is false, irrespective of what happens to the 99 different state variables, that means there are if they are Boolean, there are 2 power 99 such states. All of them have 9.0 as their value. That's what I just said. Do you see what I'm saying? Again, the interesting thing about factored representations is that if there is structure to be found in the state space, if there were irrelevant variables, if there are many states with the same value, you will find it. If not, then this representation would just reconstruct the table.
the same table.
Right? Because if you make this ADD, suppose there are 100 variables, right? If I have a 100 deep ADD, that will get me a way of writing down every possible leaf node. It'll just have 2 power 100 leaf nodes in the bottom. You can say, oh, man, I'm going to be dead now, but you're dead before anyway. You have 2 power 100 in a table. Now I'm basically going to not only require the table, but you also need the interior nodes. And your 310 data structures come to your rescue and it says, well, most of it is at the leaf nodes anyway. It's true that, so you probably are storing all this unnecessary intermediate stuff, but you are not sunk not much more at any rate. Yes? You had a question? Okay, fine. Okay, so again, this is the bigger picture we will get to some of the factor representations here. There too, actually, again, there are like multiple different ideas being tried, and I can show you some papers, but I'll give you some details at least of the current representations that people are using. Now, notice that in understanding factor representation, since we went into it that much detail, you can do two things. Okay, one is you can use factored representations to specify the problem, but solve it using atomic representation. That means you essentially take the specification in the factored form, but then you right away convert it into atomic representation and just use atomic approaches. That's the more popular idea right now, because people actually know how to solve it at the atomic level, and so when they might take the representation of the problem in the factored level, but do the reasoning at the atomic level. Okay, another idea would be that you take the representation at the factored level and you actually continue doing the reasoning also at the factored level. That means the Bellman update itself will be in terms of ADDs and 2TBNs. Okay, if you do that, then you actually need to write a new Bellman update algorithm, which depends on the internals of the representations you are using. Okay, and people are doing that too, but those are typically more sophisticated algorithms, and they may or may not always work out. In fact, I think the second class of this semester, I had a long harangue about whether it's worth doing the reasoning in the lifted level or at the atomic level. In fact, one of the interesting points I hope I made in last time is that some of the faster ways of solving first order theories is using propositional reasoners. In logic, deterministic logic, some of the faster ways of doing inference over first order theories is to use propositional theorem provers or propositional satisfiability solvers, because those are so darn fast. You still take the representation in the first order because that's much more compact, but the reasoning you do it at the atomic level. So whether you do the reasoning at the atomic or the factored level, you still want to understand the representation at the factored level, because that is somebody else giving you the representation and they may not want to write a huge big table for you. Okay? Does it make sense? Okay, so that's where we are. So I'm going to start talking about RTDP first. So I'm going to talk about RTDP, then I'll talk about UCT, and then I'll talk about determinizations, and then at some point of time I'll talk about factored representations. That's the agenda of things to come. And most of this is not in the textbook. In fact, none of this is in the textbook. Okay, right? So it's beyond the textbook. I mean, there is some places where, obviously textbook does talk about, one of the interesting things is the textbook doesn't talk that much about factored representations for stochastic side of the spectrum. They do talk about factored representations for the deterministic side because they have propositional logic, they have first order logic even. Okay, but that's partly because we are figuring that out. Okay, so RTDP. Again, right now we're going to understand this at the atomic level. Anything first you understand at the atomic level. And then, so this picture you remember from last time, and in this case you had the TD, temporal difference learning, and this is a dynamic programming based update, and I'm going to look at the dynamic programming based update, and that's what RTDP is here. Okay, so it was meant for essentially reinforcement learning. It was, the agent was acting in the real world, and essentially you would do these trials in RTDP. You simulate a greedy policy starting from the start state. So at any given point of time, you have some idea of the value function, and you are improving that value function through RTDP trials. Using the current value function, you can compute the current greedy action, because RTDP is model based, not model free. Okay, so since you have the actions, you can compute and again, most of the discussion here, of course, you are using RTDP for when you are given the full model anyway. So of course, you don't even have to worry about should I learn the model or not. The model is there. Okay. So you simulate the greedy policy starting from the start state. You perform Bellman backup on the visited states. So Bellman backup essentially tells you, it basically makes you look at all the neighboring states and take the min over the action cost or max over the action rewards. Okay, and then you perform the Bellman backup. Notice that the TD, temporal difference learning, did you do the Bellman backup? Again, remember, you should try to remember that in temporal difference learning, you don't do the Bellman backup. You essentially just make this node be closer to its immediate successor. Here, you are actually going to make this node be closer to not only the node that has been seen as its immediate successor, but also all the other nodes which it knows exist. They just have their values from the previous iteration. Do you see what I'm saying? Okay. And so you then perform the Bellman backup on the visited states, you stop when you hit the goal. So this idea is, again, by the way, in doing this, we'll assume that all of our discussion, as I said, is in SSPs, stochastic shortest path MDPs, with a initial state given. So you can start from the initial state, do RTDP until you hit the goal. Okay, now when you hit the goal, you completed one trial. Okay, and then you keep doing these trials. Repeat these trials forever. And by doing this, hopefully all the values for the states are being infinitely often updated using RTDP, the Bellman updates. And so you will guarantee you are, as the number of trials reach infinity, and if you are in an ergodic domain, that you don't die because you reach a state. Okay, then you will be guaranteed to essentially converge. Okay, and this was supposed to be a reinforcement learning algorithm. And what we're going to do is use it even though you know the full model up front. There's nothing to learn. It's just that you're going to be using the same idea rather than use the entire model with policy and value iteration. Okay?
But still there are chances that all states won't be visited.
Yeah, that's the whole point. I mean, if any states, so because you're talking about infinite number of trials, then any reachable state will be asymptotically reached. If certain states are not reached, that means they'll never be reached. Given the actions, those states are unreachable.
What is the meaning of full backup?
Full backup means Bellman backup. That means you consider for each action its expected value, and you take the best of all the actions values. So add the cost, add the reward to it, and give it to the previous state.
So RTDP is a special type of dynamic programming.
RTDP is a dynamic. So RTDP is doing Bellman backups, okay, while actually visiting states. Okay, so it's not updating everybody's values. It's basically visiting a state, and based on that state's value and the previous values of the other states, it's updating its current value. See what we're going to look at an example. Okay, now as I said, we'll assume that at any given point, even from the beginning, there's a value function that's initialized. And if you have no better idea, then you can assume that the value function is initialized to 0. Okay. By the way, the other important thing to remember is for this whole time, we'll be thinking in terms of values being, the smaller the value, the better, because values are really costs. Because SSP thinks in terms of costs. Okay, and so instead of maximizing the expected reward, you minimize the expected cost. Okay, and we did this point that cost and reward can be always converted back into one to other. So we'll just discuss everything in terms of cost ideas. Yes?
So whereas before when we were talking about reinforcement learning, that was the agent actually performing these actions, now we're using the complete model that we've been given to simulate these actions?
Exactly. Okay, that's exactly what we do. Okay, now the interesting thing is, so it's a no-brainer that anything that RL can do, we can do, because we have the entire model. The question is, can we do better than what RL could do? That's something that we'll talk about in a little while. Okay. So here is a reasonably complex MDP. By the way, all we are saying here is this is the full MDP state space. Okay. And here you start from S0, and you can do this action, then you'll get to this state or this state. And if you come, then if you are at this state, you can either do this action or this action, and this action will take you here, this action will take you here. That's the basic representation. So the squares are the actions. The squares are the actions, okay? And then when you decide to, when from S0, if you were to do this action, then essentially that will either put you in this state or this state, depending on its whim and fancy. That's the probability. That's the stochastic transition part. Okay? And so this, by the way, if you look at this, one interesting thing is mentioned here, I mean, again, I didn't mention it enough, with enough emphasis, but this is LAO star, and that's kind of AO is important there, and R graph. Okay? And if you look at deterministic scenarios where A star search works, it works on what are called R graphs. Because every action essentially just takes you to a specific state. There is never any squares. Even if there is a square, there is one incoming node to the square, one outgoing node from the square. So it's really all R graph. Okay, when you write MDPs as a state graph like this, they become an AND OR graph. There are at the states because you get to decide which action to pick, and there and at the actions because nature picks either one of those alternatives, and so you really have to do expectation over both values. So in some sense, the LAO star really actually generalizes an AO star approach and our graph search algorithm to deal with MDPs, which we won't talk about. I'm just mentioning now that it looks so clearly, it looks like an AND-OR graph. Okay? But we're going to look at this AND-OR graph, okay? And then I'm going to talk about how trials work in this. So, for example, I might start from S0, start at the start state, because there is an initial state. That's the advantage. Just like A star search, these also have initial states. Okay? You start at the start S0, you right away perform a Bellman backup. We'll assume that everybody has values, so you essentially perform a Bellman backup based on the actions. Okay? Then you, so because you have basically, if you want to do a Bellman backup for S0, you need the values of these guys, because these are its neighbors. And these H values, the word H, the letter H is supposed to make you think of heuristics. Heuristics are, for A star search, heuristics are supposed to be what? They're supposed to be a bound on the optimal cost. What kind of a bound do you want for heuristics? What's a desirable bound? It's the lower bound on the optimal cost. We will assume, in fact, all the beautiful properties for this RTDP will depend on you having an admissible heuristic. Now, if you set everything to 0, that would be admissible. So it's not really the end of the world for me as far as I'm concerned. Okay, but assume that I have an admissible heuristic, I would then seed the value function with the admissible heuristic value. This also goes back to something I mentioned at the end of MDPs, that MDPs are connected to A star search. And in fact, even though A star search doesn't have a notion of policy, it just has a line plan, that's because once you start from an action state, you will never go to any state other than the state that that action takes you to. So all you ever will need is a line of states taking you to the goal state. So you never need to think in terms of policies. Okay, but you do have value functions for A star, and in particular you want to think of value functions in terms of H star, which is the optimal perfect heuristic, and H, which is the lower bound on the perfect heuristic. Okay, so if you have a lower bound heuristic, then I may have just sort of put those values on all the states in the beginning. Let's assume that. Okay, except for the goal nodes, for which we know what the values are. Okay, then essentially now if I want to update, Bellman update for S0, I have all the values for its neighbors, and I know the full model because I know the actions and their probabilities of taking me to those variables, to the states. So I should be able to update this guy's value based on these guys' values. Now you might ask, if this is all heuristics and you had a heuristic value for S02 before, how come when you update, its value will change? You have to think about that. Actually, heuristics can very well be myopic. In fact, to get a cheap heuristic, which doesn't take as much a time to compute as the perfect heuristic, you would essentially do myopic heuristics. Okay? And so when you back up your children's heuristic values to you, you will get a better value for you than what the heuristic would have told you. And to kind of increase that intuition, if you don't think for a minute in terms of game trees, because you can also think of this as game tree. Okay? Where each action is you pick the action and then your opponent is picking the outcome. That's actually going to happen. So you do min-max search in game trees. And in the game trees, you apply evaluation function at the leaf nodes. Okay? But the evaluation function doesn't have to be just applied to the leaf node. It can be applied anywhere. Why do we go deep? Apply the evaluation function and back up. Again, the same reason. Basically, evaluation functions, if they are easy to compute at all, they are probably myopic. And so, actually, going deeper and backing up will always try to improve your estimate. Okay, so that's the Bellman update up there. Okay, having done this, now what I'm going to do is I'm going to give it a word. Give this MDP an actual word. That means actually do some action. Okay, according to my current valuation, then I can ask what's my greedy action from S0. I can compute that, right? Let's say that's the action. Then I will basically, so I'm here right now. I need to figure out what this action will do. Normally, if you are solving this in the real world, you do the action and then the nature would tell you what happened. Here, you don't want to go into the nature because you have everything in front of you. So all you need to do is suppose this is a 0.7 and this is a 0.3. You know these numbers because the actions are specified. So you take a biased coin which comes heads with 0.7 probability, tails with 0.3 probability, toss it. And if it actually comes heads, you say S3. If it comes tails, you do S4. You have to actually toss it. You can't just say, it's 0.7, so it's like, I'll assume that S4 will occur all the time. That's basically not right. So you are sampling the action. Do you see what I'm saying? You are sampling the action. Okay? So you sample the action in this particular case. That's what this thing is. And so I sampled the action and suppose S3 was what my task told me. Okay? So now I just redo this whole thing now. I'm at S3 now. Okay? So update values of S3 based on its neighbors. Okay? Now neighbors for S3 are these. Now I made this actually a nice directed graph, so when you are in S3 you can only do either this action or this action. Right? And so this will get me to this and this will get me to this. Their values are from the previous time. Okay? And then I update, Bellman update, I will get a new value for S3. Based on the new value for S3, I will compute also the greedy action for S3. Okay? Greedy value for S3. And to compute the greedy value for S3, basically, let's say this is the greedy action. So greedy action for S3. This is, let's say, the greedy action. And this is the deterministic action. So there really isn't any reason to toss the coin because it will come with 1.0 probability heads, but I'll toss the coin anyway. And I'll get to S6. Now when I come to S6, again I do the same thing. I will basically first update its value, and then from S6 I can either go this way or this way. And let's say the greedy action makes me go this side. I toss. Toss again doesn't mean anything in here because this is a deterministic action. I'll get into SG. SG is a goal node. For every SSP there must be for every stochastic shortest path algorithm there has to be a goal node, remember? The SG is that goal node. So at this point now I have reached goal. Now I start all over from S0 again. And I keep doing this. Okay? Yes?
Do we incorporate a maximum depth to look just in case we get into a cycle?
Those are all the improvements, all sorts of things you can do. First of all, there is no notion of cycle, right? Because every time you toss a coin, you will get a different outcome. Okay? You can put in fact, you can do RTDP with horizon limit. And that would be your depth. You put a horizon limit, that means every time you will only do up to 15 actions. So if you reach goal before 15 actions, you are done. Otherwise, you will start all over again. And in fact, there is an RTDP variant with, finite horizon. That's a good question. And in fact, they're all connected, obviously. This technique can also be used for finite horizon applications. If you don't have any depth issue, then it's indefinite horizon. And so you have to keep going until you reach the goal.
Or enter a state that you can't. So
okay, so that's an interesting point. It turns out, does anybody, so your worry is that you'll get into a state from which you can't get out.
for instance, when we performed the first action.
Wait. Does anybody remember whether SSP allows states from which you can't get out?
There's only one such state.
That's the goal state. We carefully avoided that by definition. Okay, because remember, we needed that requirement. That's a very good point. I mean, you need to worry about this because I just threw in a whole bunch of additional terminology in the last 3 weeks. And you have your own intuitions. And your intuitions will say there can be dead ends. And in fact, SSPs don't allow dead ends. Now, why don't they allow dead ends? Why did we go out of our ways to not allow dead ends? Because if you have dead ends, there's not going to be any proper policy. Right? Why is proper policy important? What's a proper policy? Proper policy is a policy such that if you follow that policy, you're guaranteed to reach goal with 1.0 probability. If you have dead ends, there may never be any policies that will reach goal with 1.0 probability. Again, this is 1.0 asymptotically. If you live long enough, you will always reach goal state. But if you die in the middle, you won't reach goal state. And so we actually went out of our ways to avoid dead ends from SSPs, and so you would not have your problem.
So the example shown is incomplete in that case.
What?
There are sync states other than the goal state.
Ah, yes. S8, yeah.
That's S8.
Yeah. Yeah, S8 is a problem. I mean, let's hope that SSG. S5 is also the same situation.
And S7.
Yeah, I know. Yeah, this picture is better. Okay. But again, theoretically, SSPs are supposed to not have dead ends. And the way you can get out of that problem is to leave them but have a very high negative reward. I mean, very high cost. It's sub infinity. Okay.
How is this different from TD1?
You tell me. I mean, these are all the things that I can ask you in a midterm, right? I mean, just here is the thing, here is algorithm 1, here is algorithm 1. Why is it different?
Because,
and these are all, so the first time you read any of these algorithms, it looks like it's all mishmash of the same idea. Some backup is there, right? But then there are different kinds of backups. And figuring out which is very important. TD backup does not depend on anybody other than the state that you actually looked at. So had you been doing TD, S0's value would only have been shifted a little bit so that it will come towards S3's value. That's all. It would not have seen S1, S3, S2, S4.
Yeah, because it takes only consideration to which it goes.
Exactly. And that's the thing. And you might say, if you have everything, why don't you do it? Well, again, there are interesting trade-offs for doing that kind of backup. So that's that picture, right? But anyway, that picture. So this is shallow backup. I'm sorry. This is
sample backup.
This is sample-based backup. This is full backup.
Right.
Now, in fact, UCT, which I was hoping I'll do today's class, but I won't. I won't because I'm already at 5:30 and I have some more stuff to do for LRTP, for RTTP. UCT does TD based, essentially, almost TD based, because it's a sample based backup. Okay? Okay, so you understood how RTDP works, right? Right. I mean, and basically, all you're doing is you're using the model to actually, instead of doing the act, let the world tell you what to do, you're doing the model. Now the question, of course, is, can you do better than RTDP? So your friend is applying RTDP to the real world. You have the full model. You're applying RTDP to the full model. Can you do better than your friend? Can you do, I mean, of course, assuming ergodic domains, neither of you will die. Can you at least get the optimal policy faster than your friend can? That's the issue, right? Because you have everything. All you have going against you is your laziness, because you don't actually want to do policy and value iteration. Now, of course, laziness sometimes is a virtue. In fact, it turns out that full value and policy iteration on large MDPs will be being eager. And they actually are slower computationally than something like RTDP. Why? Because RTDP will only look at the part of the state space that you will actually reach. Furthermore, if you stop RTDP, you got sick and tired of it, I'm just going to stop now. Right? And then just basically whatever is the current backed up values at various places, that's your best backed up value. Based on that, you have the greedy policy. What's the likelihood that that policy is closer to the optimal policy? It's higher, because you are essentially picking what an action does by tossing the coin. That coin takes the probabilities into account. So it is updating those states which are likely to come. Remember, there was this idea of prioritized sweeping we talked about, where, rather than every state being updated every time, update some states more often. RTDP is doing this. That's why it can be faster, even though it looks like a lazy bug. Okay, so it actually is faster, and that's why we are spending time explaining this. Now, everything is fine, but at the minimum, I want to use the model I have and improve the properties of RTDP somehow. Okay, right now, all I can say is, instead of actually doing it in the world, I'm just tossing the coin. I'm assuming all of you know how to toss coins in a computer program, right? You can use uniform, the random number. Okay. Okay, so can I improve this? Now, that's what I'm going to talk about in the next 15 minutes. And that's actually what I'm talking from now on could only be done because you actually have the model in front of you. Okay? So anyway, here is the algorithm for RTDP family of algorithms. So you start with S equal to S0, you basically revise the value of S, then based on its neighbors, using a value update, then you pick the greedy action, and then you pick the state S dash such that, basically the probability that when you do that action, you'll get to that S dash is greater than 0. Otherwise, you don't care about that action at all. Now, the way we did it is we actually tossed the coin. The best we did was basically we tossed the coin such that the higher probability ones are more likely. Okay? And then you kept doing this, and then basically whatever the new S dash, you made that into S and you continue. First of all, you notice this is not a particularly hard algorithm to write on top of what you already have. So you can actually, with a couple of lines of code, throw in RTDP on top of value iteration and see which one works better if you know the initial state. Okay? Now, until some termination test. Normally, there is no termination test until you get sick and tired of it. Okay? But what we can do is we want to do at least two things. So one is the termination test. The other is, can you pick S dash such that it is slightly more informed than tossing the coin? Such an interesting and sort of counterintuitive thing. So basically, we assume that the nature would have picked the outcome that will come based just on tossing the coin, because it has a different shiny coin and you have your own different shiny coin. You're tossing the same, same kind of a thing that nature is doing. But you know all the probabilities. You also know which states have been seen more often versus less often. You also kind of know which states are farther away from their optimal value than which ones. Okay? And if you take that information, maybe you can do better than just tossing the coin. And we'll look at that later. But actually, in fact, the intuition there is for any state, you can compute what's called the Bellman update, Bellman residual, which is, so there is V star, which is the optimal cost from every state to the goal state, okay? And then H, which is a lower bound on V star, right? Because admissible heuristics are lower bound on V star. At any given point of time during RTDP, the current V is an improvement over H, but it's still below V star. So it's a lower bound. It's also possible sometimes to come up with upper bounds, probable upper bounds. Suppose I gave you a probable upper bound and a lower bound, then the difference between the upper and lower bounds can be seen as the gap that the state has to traverse to reach its V star. And one idea basically is to then multiply the probability by the gap. And the ones which have higher gap will be picked more often than the ones which have lower gap. Because the ones which have lower gap, they're almost close to their real value anyway. To be able to do this, you need not only a lower bound heuristic, you also need an upper bound heuristic. Of course, I didn't talk to you at all in this class about where to get heuristics, but from 471 you have some ideas about how to get heuristics. Heuristics come from relaxations of problems. Okay? But that's one idea for this, but I mostly want to focus on this, the termination test. That's a cute thing. And the idea for the termination test is basically, first of all, you realize that since you have an admissible heuristic, it turns out that whenever you do Bellman updates on an admissible heuristic, it will still remain admissible. This is actually a theoretical property. If you started with an admissible value function, and you do Bellman update, it will still be admissible. That means it will still be a lower bound on V star. So heuristic doesn't become inadmissible because of the Bellman updates. That's good. Okay. And then also for every action there is a Q star, Q value. Remember we talked about Q values for every action. The optimal Q value is the value that you will get by doing action A in state S. And the current value that you pick, the current valuation for that action is always going to be a lower bound on the Q star. Because again, we are talking in terms of cost. Now, that much is fine. The thing that these things will tell you is that there is a method to the madness of how value functions converge over the states. Sometimes you will know that this state has already converged. Even though the value function hasn't converged as a whole, for this state, it's not going to change anymore. When you started, you at least know one state like that, right? Because it's an SSP, all the goal states have converged already. Okay, so you label them as solved. SG is solved now. What I want to do is, as part of my RTDP procedure, I also want to propagate the solved label. And when S0 becomes solved, I'm done. So then all I need to know is, how do I propagate the solved label? Here are some cases I'll show you, and in fact those are actually sufficient cases. I'll give you a paper, by the way, you can read on LRTDP, which will give you all the details. And it's a very nice, easy to read paper actually. Okay, so you start with SG. Suppose you have a state S. Okay, suppose it turns out the current best action for S is this. According to the current value function, the current best action for S is this. Suppose it also turns out that all these Q values are higher, obviously. I mean, that's what it means, right? Basically, if this is the best action, that means these guys have higher Q values. This is the part of the tree that includes S and SG, the part of the state graph that includes S and SG. Do you see any reason why S might change its value? No, never, never, ever, ever, right? Because it already knows its best neighbor is SG. SG knows its value. So its backed up value is based on SG, essentially. Okay, so it's basically nothing could have come It would not take these actions, and nothing could have come from these actions to change its mind as to what its value is. So because this is solved, now S is solved. Okay, now it doesn't even require that SG is a goal node. If in fact S already has the label solved, and there is another, this node has the label solved, and this node has its greedy action taking it there, and every other action is already probably bad right now, then I don't need to go this, don't need to do anything further for this state. So it's already labeled solved. And if you have solved states, don't go back to them, and then you use them mostly to back propagate solved label all the way to the top. Turns out actually the solved labeling is connected to the notion of and/or search. You know, that's where, you know, in the traditional and/or search, which you probably never heard of, because it's not done in Intro to AI, unless you did somewhere else. There you actually talk about sub-problems being solved, and how do you propagate the solved labeling for the sub-problems into the composite problems. And that's sort of what you're doing here. This itself is a simple idea. Okay, now in general, what I really want to say is, of course, in the beginning, any state SG. So basically, you talk about the residual of every state, Bellman residual of every state. Bellman residual of every state is its current value, okay, minus what would be its value if we were to do a Bellman update right now. Okay, because this is the part that you would do if you did the Bellman update. And if that difference is small, then essentially it's less than epsilon. In this particular case, actually it's 0. If it is less than epsilon, then I would say it's converged. Because supposedly I'm trying to, let's say, find a value function that's within epsilon of the optimal value function. And if this guy is within epsilon, then it's converged, and then you go for everybody from above. Okay, so that's what you wind up doing. And of course, I just essentially, you could do this just in terms of the residuals, but here I just showed it to you pictorially. Okay, now there are more interesting cases though. What if I have S? So previously it's too simple. S just goes directly to SG. What if I have S, but it then gets you an action which can either take you to SG or S dash? Well, if both SG and S dash are solved, then again S is solved. It's just a little more general than the previous one, but still doable. Okay. What's more interesting is this scenario, where not only S dash has other actions, S has other actions. It turns out S dash also doesn't have any better guys. It is thinking if at all I'm going to improve, it will be because you change your value. And S says, well, I am really waiting for you to change your value. Otherwise, I can't improve. So then both of them and say, hey, we're done. Neither of them could have said by themselves, we are done. I'm done, I am done. But they two together can say we are done. Do you see that? Because of the connection. S is connected eventually, the value of, backed up value of S is eventually connected to the value of S dash, which is connected to value of S. This is where actually the normal AO star idea doesn't work. Normal AO star basically starting with the big problems and different ways of splitting into smaller sub-problems. So you can take this problem P, and in one method you can split it into P1, P2. Another method you can split it into P1 dash, P2 dash, P3 dash. Another method you can split it into Q1, Q2, Q3. And then each of these problems can be sub-split again and again, until you reach problems that can be solved and you know how costly they are. Then the question is, what's the best way to actually decompose the top problem? So the lowest cost way to cheapest cost way to decompose the top problem to solve it. That's the normal AO star. There is no cycles, right? Because if you essentially take P and you decompose it into P1, P2, and P again, what does that mean? That doesn't look like an actual decomposition of a problem at all. You see what I'm saying? But however, even though AO star analogy works here, these are cyclic graphs. Okay? And in fact, and that actually comes up here, neither of these states can independently say we are converged, but both of them together can say they have converged. In general, the problem is a whole set of states can together say we are converged. That's a costly description, costly way to figure that out. But if you figure this out, the advantage is now you are propagating the label, solved label, greedy way versus non-greedy way. So if you are spend some time and figure out like pairs of nodes that are together converging, then you have named both of them solved, and because of which some more things will get solved, and so you'll get solved at S0 and you're done. Yes, sir.
How often does the entire thing basically all converges goes solved out once, and as a result it costs more than
I didn't get the question.
How often does it just end up converging all at once? I mean, solving all at once and end up costing more?
Sure, extremely lucky, I guess. I mean, for that, first of all, you need to. One way that could happen, for example, is if your initial H is V star, then it should happen. That's at least a case where it should happen. But by the way, these are good questions. Given that it's evening and you may not have heard about this before, all these are good questions. It makes me think that people are actually getting some of it. And then you read the paper, which, this is the paper I'll ask you to read for just this algorithm. Okay? But let me complete, because I think people are waiting. Let me symbolically complete and say, essentially, LRTDP does the normal RTDP, but it also does label propagation. Where label propagation is this procedure I described, and that itself can be written as a little algorithm. Okay? And if you do that, then it converges much faster. It converges much faster than normal RTDP because it avoids wasting time on states whose values are not going to change because they've already converged. Okay, now this you could not have done if you are doing reinforcement learning because the world never tells you, by the way, this state you know everything about it. It will never tell you that. Here you know because you know the actions and their outcomes. So that's where you are actually kind of using the model to propagate the labeled function. And this picking successor is what I mentioned earlier. You have both backups on upper bound and backups on lower bound, and then you can pick a sample that's based on the probability times the gap. That will improve even further the speed of convergence of this. Okay, this paper that I will send you, which you can read just to understand today what happened in today. This is like the textbook description for this particular algorithm. Essentially describes up to the labeling process, not this stuff. There's a lot more other improvements people have made, including this and more other things. But but this will give you a feel for what you're able to do by using the model as a simulator, and using the initial state, and using the heuristics that came from A star search site. Okay. So actually I would suggest that to make sure that you actually read this, I will say, I'm going to give this to you as soon as I go back. I'll send you the link, and I would require that everybody writes a short review of this, especially focusing on things that I didn't say here. The stuff that I said. Okay, on the forum. That's a required homework. See you tomorrow. See you on Wednesday.